Hmm. Hmm. I had a huge a diagram that I was going to come here early and write it on the board, just listing all the groups that one would hope to find explicit conjectural formulas for. But I'm not going to take the time now to do it. I'll try to come early to the next lecture. And so actually for the next lecture, if with your forbearance, I'd like to give, this is the last week of lectures, but I'd like to, I think I've already said I'd like to lecture Wednesday at 11, as well as Wednesday at 5. And the Wednesday at 11 would be to discuss Vé groups. That'd be more elementary and a slight change of pace. And then, if possible, I'd like to meet twice on Monday, if that's agreeable. And those would be the last two lectures. And maybe I'll just do it, and because they'll be on. Is that okay with you, Pramath? Or you're leaving at some point?
I'll try to.
Well, you don't have to. You know, there's no. And it's online, so you can see it. So let's just say lectures. Wednesday. What's the date today? It's the 3rd, is it? I think it's the 3rd. So Wednesday, April 5th. That'd be 11 to 12. That room is free. And also Bayan. And 5 to 6. Fields. And then also Monday, April, university's closed on this coming Friday, but then Monday, April the 10th, also at these same two things. Walid pointed out to me that actually what I did last time, maybe I will make, this is a pause for motivation, explaining why I'm doing what I'm doing by talking about periods when we're supposed to be defining conjectural structures of these exponential groups. So here's a pause for motivation. I think I've talked about it. This is just coming in the middle of out of nowhere, and then I'll talk about the thing I wrote down wrong last time. But so pause for motivation. What I want to do is to find conjectural versions of new groups and what would these be? These would be exponential. So I'll just draw where these were going to be in the big diagram, which I'll try to get there early on Wednesday morning and write it on the board. But so we've already talked about a possible formula for the just a minute. So these would all be new groups. This would be This would be the exponential pure motivic Galois group, and we know something about that. Not a lot, but we know something about it. We know the analog of the Tanyama group, which is a bigger group, actually. So I'm not going to talk about it much now. And then there should be, presumably, I'm going to write the mixed version of this, as I think we have done with regular motives. I'm going to put a plus. So the tilde means like a covering group. We haven't used that notation before. This would be a covering group of this would be a covering group of the group never mind. I'll sort it out here. So this would be the exponential motivic Galois group, mapping into the Tanyama group, and then we would want a mixed motivic. We'd want, to be honest, I have done. My preparation is so lax, I'm not sure what we would do for this. I'm not sure that I have a guess for this. But in any case, this would be the mixed motivic. This would be the mixed motivic, exponential motivic Galois group. This would have another piece to it. Okay, so that's what we would like. But in any case, if I'm going to try to talk about that, I can't pull it out of the air, because what exists for this thing? There's stuff that does exist for this thing, and there's a limit to what I can say about it, partly because of my shortage of time and because I haven't really prepared it. But what exists, at least for this group, are periods. There's a long book by Frisson and Josson about what these exponential periods are. So that's why I am talking about periods, even in the case that we have already talked about, the regular motivic Galois group and their periods. That's why I'm talking about the periods first, and then just adding a few remarks to say that you could think of the periods first, and then I'm not sure that would, what I'm about to say would uniquely characterize the groups, but think of the groups as something that you introduce as an afterthought once you've got the periods. And we already know what the periods are. We have this informal definition of Kontsevich and Zagier. They give a definition of a period, a very general definition, and in the most elementary of terms. So we already know what those things are. We also, presently I will just recall or say what their generalization of that definition is for exponential motives. So we have to treat exponential exponential periods. So we have to treat exponential periods as something that's already given to us, and then trying to find this group that somehow is attached to them. So the exponential periods. So anyway, I will do that. Now, Walid pointed out to me that if you have varieties, this is the category of varieties over F, and F's a number field, which is contained in the complex numbers. This is asking a lot. These are singular varieties. This is any kind of variety, but Durham cohomology would map this. So what I was wrong, I said it was going to map it into a vector space over Q. It doesn't do that. The varieties themselves are only defined over F. So given a differential form, on the complex variety, Grothendieck's theorem tells you how to, and I gather it's a very deep theorem, but Grothendieck's theorem tells you how you can make it descend to a differential form on the field F, but you can't go below that, which is what I indicated, which was what I wrote down wrong last time. So this maps into vector spaces this is the deep theorem of Grothendieck, whereby the differential forms that define de Rham cohomology actually can be taken over this field of definition of the variety and not the complex numbers. And so this would map into vector spaces over F. The Betti cohomology, that's much more forgiving. So this is H star Betti. It gets to have coefficients wherever it likes. And so that would map in particular to vector spaces over Q. And one would want to compare these two things. So what you have to do is you have to take the tensor product of this. Tensor product over F with C. And that would give you, tensor product over F of Q with Q to vector spaces over C. And this, you would take the tensor product over Q with C, and that would also be vector spaces over Q. So you have two vector spaces over Q, and integration then gives you an isomorphism from these things, from this vector space here to this vector space here, both vector spaces over C. And I do want to take tensor with C, thank you. Thank you. So that's, then you get a vector space over C there, you get a vector space over C there, and what you get from the de Rham theorem, or this fancy version of it, is an isomorphism from this to this. The point is, well, it's just any isomorphism, an isomorphism between complex vector spaces. What good is that? Well, what good it is this comes with a basis or a natural family of bases over Q. This comes with something a little less desirable, a family of bases over this finite extension F. And so this isomorphism, this between complex vector spaces on the right gives what I just said, an isomorphism between two complex vector spaces with extra structure, but the extra structure is different. This has a Q basis up to multiplication by GL by GQ. This only has an F basis, and so this gives the structure of such things. That's a little more clumsy sort of a thing. This gives what seems to be called an FQ vector space, a complex vector space together with an isomorph, a complex vector space together with a linear isomorphism. Well, we could even send it to itself, but it has a Q vector. No, let's make it two different spaces, and the domain has a Q basis. The domain has an F basis, and the range has a Q basis. So this seems to be called an FQ vector space, and this kind of structure, I don't know what to make of it. It's not quite as agreeable as what you get when F is equal to Q, but this, I guess one could think about it, and I guess one could figure out before too long what sort of structure these things have. But anyway, there's a whole section of this in this book that I mentioned last time, a 300-page book on periods and Nori motives, section 5.1. They study these things. So I won't say anything more about that. The thing is, this is also supposed to match motives, a motivic Galois group that has coefficients in F rather than Q, which is the sort of setting that we that is the setting that is natural for this. But let me just add, I can't remember whether I talked about this last time. The most important special case is when F is equal to Q, where we get an isomorphism. H star Duram. So I could tell, I can let me take X just for simplicity. I'll take X not to be an arbitrary variety over Q, but let's say a projective smooth variety over Q. And so H star Duram of X, C, that's a complex vector space given by H Duram star X. And now Q, not F, Q, and an isomorphism between H Betty star X, C. By definition, yes, sorry. So I don't have room with that there. This would be X, a projective variety, a smooth projective variety over Q. And this is the tensor product of this with C, and then that is an isomorphism of the same thing with Betty cohomology. H star B X C equal by definition to HB, or close to definition, HB Q tensor C. So I think, I can't remember if I talked about this. So this is between complex vector spaces. Both of which have Q bases. So that's much more agreeable. So we can just take the matrix. You got a map from one vector, an isomorphism from one complex vector space to another, and you pick a Q basis, of which there's a canonical family of such in both of these vector spaces. And at least for those choices of Q vector spaces, you have you can take a matrix. And so you could say that the matrix of this isomorphism with respect to any two bases over Q is called the period matrix. In the end, you just really are interested in the linear space, the Q linear space, spanned by the entries of this matrix. That way it doesn't depend on the Q bases that you took. So whose entries span the resulting Q vector space. So you just take that matrix. It's going to have complex entries in it, n squared complex entries, and those entries are what are known as the periods. They're the periods attached to the given smooth variety X, and if you want them to be independent, if you want something independent of the bases, you just take all of those entries and then take the Q linear space spanned by them. So span the Q linear space. So the Q linear whose entries span the Q linear vector space. So by definition, you take the Q vector space spanned by the n squared complex entries in this matrix, and this would be called, well, this is what we'll write this as the periods attached to X. If we want to keep the Q in it, we could say PQ of X. But whatever it is, it's a vector space, a linear space, Q linear vector space, finite dimensional as a matter of fact, contained, it's a Q linear space of numbers, periods, that's what we call the periods, which is complex numbers. And these are called effective, the word effective is silly, kind of a silly word perhaps, but pure periods for X. We'll get rid of that in just a moment. Or periods over X, do I say over X or for X? And then the union, you would take the union P, let's call it plus, and I'm going to write effective there. I guess I should write effective up here. One stops writing that after a while, but I'll just say what you need to do to get rid of it. But P plus effective, or PQ plus effective. And I'm putting a plus there because all of this goes through, and the theorems of the Grothendieck theorem is the main one about letting the de Rham form descend. But my understanding is that it all goes through for not just smooth projective varieties, but for any variety over Q. So you take these definitions still work, and the union of these things, so this be the union. You have an infinite union, countable union of vector spaces, finite dimensional vector spaces over Q, ranging over varieties, and these are vector spaces of complex numbers, rational vector spaces of complex numbers, so that when you have infinitely many vector spaces, you don't take the direct limit if you're not worried about the topology on them, you just take the union, and so this would be P X Q. Put the Q in, I don't really need to. Effective, this is contained in C, is the infinite dimensional Q vector space of all effective, and I could then say mixed periods, because I'm not just using, I don't know if that's the standard term, but I'm using mixed, they would correspond to mixed motives. Mixed periods. And as a matter of fact, one can observe it almost immediately that it's not just a vector space, it's an infinite dimensional vector space, but it's actually an algebra over Q. So one then observes, because if you multiply two periods, then you're going to be able to do this all over again for slightly different vector spaces, but in slightly different objects. But so one then observes, one then sees that it is actually a Q algebra. So very nice structure, just as handed to you. All these complex numbers. So, and then I'm going to just say similar arguments apply to the case that is messier, apply to number fields, field F, and we get the algebra PF plus effective. So this is motives with base F, but it's still going to be a Q vector space, just like we had with varieties and motives. Usually you don't write the Q. Plus effective. I'm putting a plus on this to match our notation for the groups GF, motivic Galois group, and G plus F, because the mixed motivic Galois group. So just in my own mind, I'll try to keep everything straight. I'm going to put a plus on the periods as well when you're talking about mixed ones. I don't know if that's standard notation or not, but the union over varieties X defined over F of P plus effective F Q X. And again, it's an algebra over C of effective. F periods. I don't know if I was going to remark on this now, but these are like numbers that generate a field. Or it's almost, I guess if you take the Q algebra, it's almost the analog of a field itself. And you have a group, if that's supposed to be like a field of complex numbers, it's not a field, it's an algebra, but if you are going to think of it as an algebra, then you might want to think of the motivic Galois group, or rather its Q points, as a Galois group. And indeed, it does act on the algebra, almost like a Galois group. And that's why it's called the motivic Galois group. But in particular, if F is a field over Q, finite extension of Q, if this is Galois, then, and I think I'm right, I think this just follows from the definition, PF, the periods, mixed effective periods, it's smaller than the algebra of periods over mixed effective periods over Q, or rather, it's a quotient of it. This thing is the same as the periods, effective periods over Q. I'll put the Q in there. But rather the set of orbits in that thing by the actual Galois group, the Galois group of F over Q. So these stand for Galois orbits. So if you tried to draw, I'm not going to try to do it, but if you drew a diagram of these things, I think this is right. It looks obvious to me, and but I don't, not sure I really found it anywhere. And if I have concerns about it, let me know. But I think that what happens is then you can make diagrams just like you do in Galois theory, where you have a lattice of fields and a lattice of Galois groups. And you'd take a lattice, well, let me get rid of the effective. I really want to get rid of the effective, but I'll just talk about it in this case. If you have a lattice of periods indexed by fields F, then you'd have a lattice of Galois groups, G plus F, or Q points of that. And then the quotients of those things you don't take the quotients of those things, you'd take this for the quotients. So I'm not going to try to write down a diagram of the kind that we teach in Galois theory, but it looks like there are diagrams for these things that are similar to what one has in Galois theory, except you don't. There's two kinds of Galois groups that would occur in the diagram, whereas in Galois theory, you have only one kind of Galois group. This is understood to be the Galois group of F over Q. Maybe I'm supposed to be writing that as gamma of F over Q. Don't want that to be confusing. It's just the ordinary Galois group. Orbits of that in here. So you'd have, be like if you had a diagram of groups, all of the quotient groups in the Galois correspondence lattices, all of the quotient groups or the intermediate groups would be these guys. And the analogs of fields would be these things, but then the Galois groups of each of those over the algebraic closure would be the big groups, if that makes any sense. GF. Okay, so just one final note. This is completely parallel to what one does in motives. One defines Grothendieck defines effective motives by I'll maybe just say a word about it in a moment, but he defines effective motives by his standard conjectures and construction by means of algebraic cycles. And then that's not quite enough. Those are effective, I think maybe means natural, or things that are more concrete. Anyway, what I'm about to say is the complete, this is the effective periods are the complete analog of what are often called effective motives. And to get all motives, you do, or all periods, you just enlarge them a little bit in exactly a parallel fashion. And in what we've got here, I wrote down a bunch of things that were periods according to the original definition of Izagirre and Kontsevich. They then persuade us, they do a good job of persuading us that the periods are exactly, as they define them, are exactly the same as what you end up with this. I mean, there's much technicalities that go into this, but they give an argument as to why the periods they defined in that very down-to-earth way that I described last time end up being these things that come from the comparison of Betti and Durham cohomology. But then there's one, and then I wrote down a bunch of numbers that were periods in that sense, and in this sense as well. So pi is certainly one of them, but pi to the minus 1 is not. And so as with motives, one simply enlarges, one simply adjoins pi to the minus 1. That complex number, real number, in fact, you just adjoin that to this algebra that you've got. Another way to say what you're doing is to say that it's the same thing as adjoining 2 is certainly a 1/2 is certainly a period, and so is the number pi. And so the number square root of minus 1, it's an algebraic number. So that's the same thing as adjoining 2 pi I to this algebra. And then this sort of resonates elsewhere. This is what happens with, this is more obvious what you're doing in the so-called Hodge realization of motives, and or in complex variables. 1 over 2 pi I, it occurs everywhere in complex analysis. And so that's the kind of the, in some sense, this is kind of the origin of it. So in any case, to define, so you adjoin that and use that to define the Q algebra, slightly larger algebra. I'm just going to write it as PF, if it's over F, plus, without the effective as a superscript, to be PF plus effective. So just a tensor product of this polynomial algebra, Q I to the minus 1. A very small enlargement of this, and that would be contained in P plus, I've got a plus sign here, equal to P, what you have with rationals there, P plus effective tensor Q I to the minus 1 of all periods. So that's what one does with motives too. You have effective motives. I'll say a word about that. And then you, what you call effective, and then you enlarge it slightly by taking so-called Tate twists of them. And it's exactly the same operation. And just as a, if you're looking at Kontsevich and Zagier, I don't think they ever mention F in this. I think they always take F equals Q for simplicity. Okay, I'll do that. I'll take this down. And so okay, so I just want to say a couple of words. I'm trying to motivate how you would, in some sense, how you would construct motives and motivic Galois groups from periods rather than the other way around. It's usually presented the other way around, I think, but I think we're forced to do this when we want to talk about exponential motives because we have this large book on exponential motives, and they define the notion of exponential motivic Galois group, but there's nothing explicit in that, whereas their description of the motives is very explicit. So I think we have to think of things for this next step in those terms. So I'm just going to say a couple of words. I don't know whether Grothendieck thought of periods before he thought of motives, but I'll just say this would have certainly been a part of his reasoning. The definitions are constructions that we have just gone through. Given by what? Given by, have I rubbed it off? I've rubbed it off. I won't write it down again, but I'm talking about the diagram that that come from the diagram. See, I'm very well organized here. I spent too much time in the last couple of days trying to understand Mekavar's article. And oh yes, it's this diagram here. So X, let's say X is a variety. H star the RAM cohomology maps that to vector space over F. Then you tensor I guess I won't take X there, but you tensor that with C to get a vector space over C. You do the same thing with Betty cohomology. Vector space over Q, which you tensor with over Q of Q to get a vector space over C, and you then have an isomorphism of complex vector spaces, and as we've sort of described there, how it gets periods. So Grothendieck's reasoning might well have been, surely was, the definitions and constructions that we've done there, given by that diagram, are rather coarse. I mean, they look, if one believes all this stuff about Grothendieck's de Rham forms descending to F and so on, or Q if you're going to just deal with things over Q, it looks, pretty nice, but really it's rather coarse because you'd be talking about all varieties, and all varieties, who knows what the average of a variety is, but it might be of 1,000 dimensions. And so you'd be talking about the cohomology of a 1,000-dimensional variety, and it's very, even just by taking out the weights. Well, let me just say, the definitions given by the diagram are just going to send huge wallops of periods at you, which are kind of hard to organize and make sense of. It depends only on the cohomology. H star, I can't remember, I don't know if I talked about this, H star X of a variety, X. Well, for a start, you could break that down a little bit. You could take the degrees or weights. Degrees or weights of a variety, or of the cohomology, the weights Hn of X of cohomology. And so you get a finer structure. That gigantic matrix of periods is going to break into blocks, and i.e. smaller period matrices. So that's already a step in the right direction. But Grothendieck would have said, oh gosh, you can get a lot more than that. And then the cohomology groups themselves Hn themselves can have a still finer structure. So I'll just say that this is governed by algebraic cycles. The algebraic cycles within on a variety governed by algebraic cycles, or if you prefer subvarieties, on X. Okay, so these thoughts, this governed, this was at the background. Growth and peaks. Conjectural. Construction of motives. Motives would be the smallest piece of a given cohomology group that you could single out by what the periods cut down give you. They lead to, so they lead, I think I mentioned how you increase the morphisms between varieties by using cycles, taken up to homological or numerical equivalents. And so they lead. To a refined, actually abelian category, Q-linear, Tannakian. And there's standard conjectures that nobody's proved them yet. They seem untouchable, that lead to the right structure here, but from cycles, but we could call it mote F plus, that replaces, it's got a finer structure, the category of varieties over F. And then the choice, so I'm combining a couple of steps. This first of all leads to a category of effective motives, and then you have to tensor it with, the Tate twists, make it a little bit bigger. That gets can have negative. These degrees of cohomology are always positive, and you want something that to get to this, you want something that has negative degrees as well. So you just arbitrarily tensor them with the Tate motive, which comes from the absolute value on the Tannakian group. It's the sort of most simple pure motive. And so then I'll just say the choice of a fiber functor. Phi, from this category of motives, this abelian, or actually Q-linear Tannakian category, to vector spaces over Q, then leads to an isomorphism of categories, or I guess it's really an anti-item isomorphism. Finally, so this is the last step, to an anti-isomorphism from the motives F plus to the category of representations of a group over Q. Okay, to the category. of representations of a pro-algebraic group GF Q plus, I'm putting a plus down because I'm including mixed motives in that. In other words, GF plus, I don't need to put the Q there, GF plus. And so then this, the rational points on that group act like a Galois group on the algebra PF. So you've got, we can sometimes, maybe we can write MF plus, maybe write it like that, and then it's parallel to, so that's like a Galois group. So GF plus Q, the Q rational points, then act like a Galois group on the algebra, on the Q algebra, P F plus. So we've got MF plus, the motives, which are the category representations of this group. Well, let's not put in the Q there. We'll have L, the notation parallel to it for everything. So the Q rational representations of that. And see, these are Q rational representations, and it acts like a Galois group on this Q algebra, this. So very, very roughly speaking, probably with some inaccuracies, but that's how one would start with the periods, and in the efforts to narrow them down to get a finer kind of diagonalization of the period matrices with these, say, given by these standard conjectures, one gets a group and which acts, whose rational points act on that Q algebra motives, a Q algebra of periods. So what we want to do is to just set things up a little bit for exponential periods, and then I'll do this on Wednesday afternoon, and then I don't wish to be too dramatic, and I hope what I say on Wednesday afternoon is not wrong, but there is another world out there, a whole nother world for, I mean, automorphic forms and automorphic representations are what give you this. They give you the explicit formula for this, hopefully correct, explicit construction of that. We've got this larger class of motives, which I'll say just a few words about, and they're written down very explicitly in that book of Fressen and Josen. So the question is, what's they say there's a motivic Galois group. I mean, they don't go to any, not shy, they say there's a motivic Galois group for that, but we want an explicit formula for it. So there's a whole nother world where it has to be there just by process of elimination. So we'll introduce that on Wednesday. It's Wednesday at 5 o'clock. We'll do vague groups at 11 o'clock. Yes, Melores.
So when you do this, like that means that there's like a lot of redundancy coming from the varieties.
The varieties, I guess, would be countable too.
I don't know. The varieties are countable.
Yeah, they have Q coefficients,
For a number field, that's
Oh, yeah, that's right.
and they have,
In many cases, like the redundancy, like somehow you lose the variety in this linear.
well, the variety, I think, is, I think, um, this was before we talked about this. So that's the algebra of periods.
Yeah, that's right. So the algebra of periods like loses the information of the varieties.
there's many different varieties that have kind of the same pieces of cohomology.
That's right. So that's the best thing that you can get. The best thing that the periods remember are the whole.
Sorry, the best thing,
The best period, like what the period remembers are the multis.
so the periods are numbers. So they, as you said, they have some common ground with each other.
Yeah, they're invariants of the motives. You have different varieties that have the same motives. Like pieces of the cohomology solution.
So we define this as the union over all varieties of this algebra of complex numbers. So there's going to be some.
Yeah, what I'm saying is like if I just look at the periods, do I forget about the varieties? Do I have hope to recover what pieces come from which varieties?
I think even the L functions are defined at the level of the motive, not at the level of the variety, right?
That's right. So there's no reason to
even remember.
The insight is that the motive is after.
So the expected thing is that I can recover if I just look at a particular piece, I will be able to recover the whole thing.
Yes, that's the whole point was, I guess, of Grothendieck was, look, let's not take varieties. They're mushy stuff all over the place. Let's get these individual pieces, the hardcore pieces of varieties, sometimes shared by different varieties. And then we get this group. After all, these are related to automorphic representations, which are related, the most basic automorphic representations that are not punctorial images from any smaller group. And then we save out the family, the the family of conjugacy classes in the dual group. And that's very concrete information. That's basic information attached to automorphic forms and this automorphic Galois group. And that's what goes in ultimately to the motivic Galois group. Some of them actually have to, their automorphic representations have to be thrown away because they're non-mass forms, they're non-holomorphic automorphic forms. They got to be thrown away. So these is basic information. And that is the governs, if this is correct, it governs all motives and as just individual, indivisible little pieces. So we want, I mean, as Walid would say, that yes, but that's not the whole story. These exponential motives are very important as well, as I understand it, for physics. Feynman diagrams, and so you know, this isn't enough. So we'll talk about it insofar as I'm competent to do so. We'll talk about it on Wednesday evening. We'll talk about they groups on Wednesday morning.